it's not. This is the coexistence region. And I have mentioned about the problem with this unstable van der Waals result. We have to correct it. Correction is known as Maxwell's construction. And it has to do with the behavior of the Helmholtz free energy. See, when we look at the Helmholtz free energy, let me tell you as a side effect the behavior of Helmholtz free energy. When you look at it, as I have drawn it, when at temperatures lower than the critical temperature, you might have a diagram like this as a function of volume. Here is the behavior in phase 1, this is liquid. Phase 2 is gas. Okay. The negative curvature corresponds to unstable curved part. Okay? In the PV isotherm. But instead of doing this, if you create a common tangent, okay, a common tangent, you get a lower Helmholtz free energy instead of the negative curvature. This corresponds to dash portion, the unstable portion of the earlier curve. Well, if you phase separate into a region of V1, this is liquid, into a region of V2, which is gas, the system becomes inhomogeneous. That means there is a gas region and a liquid region. Well, from thermodynamics, we know that for fixed temperature, volume, and number of particles, the stable state is a state which minimizes the free energy, isn't it? Is the state that minimizes free energy. So we have to look for a phase-separated state, if you like. And that state has the following property. F as a function of volume has V1 and V2, and this is F1 and F2, a straight line connecting these two states. Well, fraction of states in the first state, x1, let's say, fraction is percentage, isn't it? x1 in state 1, x2 in state 2, so that we have the following relationship. x1 times n, total number of particles in phase 1, plus x2 times n must be equal to total number of particles in the system, isn't it? x1 and x2 are percentages. So if they are percentages, they have to add up to 1. 0.20 is 20% in one phase, 80% in other, 0.80. When you add them, you get 1. So I will come back to this curve in a moment. Free energy becomes x1 f1 plus x2 f2. Okay. Total volume becomes x1 v1 plus x2 v2. Or we can write these as follows. Fx1, this means, is x1 f1 plus 1 minus x1 f2, and v x1 is x1 v1 plus 1 minus x1 v2, and x1 is something between 0 and 1. If we change x1 in this range, we get along this line, isn't it? We go along this line from V1 to V2. We go in that direction. Huh? So if you change the percentage, you have to follow that straight line. Well, you go from where to where? From phase 1, that means V1 F1, to V2 F2, phase 2, isn't it? You go from one to other. Here x1 is 1. Here x1 is 0, isn't it? x1 is the fraction in phase 1. This is all phase 1, that is all phase 2. So let's see what it means again. How are we going to get the correction. Let's do a small calculation here. V is x1 v1 plus v2 minus x1 v2. So you can rewrite this as x1 v1 minus v2 plus v2. So x1 can be written as v minus v2, v1 minus v2, x2, 1 minus this, becomes v1 minus v, v1 minus v2. If you add them together, you have to get 1. Okay, do that. Let's write the free energy. Free energy for inhomogeneous case. Inhomogeneous means segregated. System. That was the volume for that system. x1 f1 plus x2 f2. You can write this as a linear function of volume minus f1 minus f2 v2 minus v1 v plus v2 f1 minus v1 f2. Why don't you do the calculation yourself? Yeah? Homework again. It's a linear in V. So linear interpolation is lowering the free energy, lower F, as a result of linear line or double tangent line, double tangent construction. When the straight line becomes double tangent, you have the lowest free energy. Now, let's see the meaning of this double tangent to lower the free energy by looking at the unstable region again. Is that okay? Now, let's see the meaning. We were trying to construct the Maxwell construction. This is the unstable region where you have something like this. So we are trying to get it to be a straight line. By looking at the free energy difference between liquid and gas as PdV, V1 to V2, two phases have this difference. Well, the meaning of the common tangent is that del F del V at constant T is the same for both faces. But dF, we know that it is minus S dt minus P dV. So it is the pressures, which is minus dF dV. So coexistence of two faces then is the fact that they have the same pressure as we expect. So Maxwell Collection construction equates the pressures for two faces. So what you look at, the integral of the van der Waals curve and equate them, isn't it? So that's the Maxwell construction, which takes us back to the double tangent construction. They are equivalent. So the line joining A and B, A is the liquid phase, B is the gas phase. When what you are doing is considering the area under the straight line, joining A and B. So it gives you this, isn't it? Straight line. Yeah, you are making this equal to area under van der Waals curve. Joining A and B. That means you are considering this curve, okay? So you are calculating the area under this curve, joining A and B. Make them equal means T is equal because you are looking at an isotherm. Pressures now are equalized, Maxwell construction. Now we have to discover what happens to the chemical potential. Did we understand the Maxwell construction? There are two areas, one the straight line under which we have an area, one the van der Waals curve. We are equating that. Now let's look at the chemical potential. See, I am hurrying a little bit because we have small time left. The chemical potential is Gibbs free energy per particle. So we have to look at delta G and put it equal to 0 between points A and B. Let's see, dG was minus S dt plus VdP. Since it is constant temperature, that part is 0, isn't it? So VdP, now to get the change in Gibbs free energy, we have to integrate VdP between A and B. That means the following. Integrate by parts. U and dP, you have the following. P times V from A to B minus P dV, isn't it? Well, that is simple. P VB minus VA minus VA VB P dV. Well, this is exactly area under straight line. This is area under van der Waals curve. If you put that equal to 0, what are you doing? You are equating the chemical potentials. So you are back into Maxwell's construction, isn't it? So back to Maxwell's construction. The meaning of this, having two areas equal, meaning that we are equating the chemical potentials for two phases. There is a cusp in G, so the transition is first order, okay? Second derivative of the thermodynamic potential goes to 0. Straight portion of f of v, a cusp in GV goes to infinite 2. So there's a kink in G, so the first derivative is 0. Well, as the last point for this model, we can calculate the critical exponents of this phase transition. So I showed you how to correct the behavior, okay? So it then corresponds to a real phase transition from gas to liquid. With this correction, you can use van der Waals model. And here are the critical exponents. It's a nice thing to do. Of the van der Waals model. Internal energy can be found to be 3/2 nkBT plus a n squared over volume. So this gives a heat capacity d dt at constant V which goes like 3 over 2 nkb, and this corresponds to t to the power 0, isn't it? So alpha is 0 for this. A constant means something to the power 0, isn't it? So alpha is found to be 0. Isothermal compressibility, this is 1. To the isothermal compressibility, which is minus 1 over V dP dV, that gives you something like let's calculate dP dV at V equals critical volume. We have calculated these critical values, remember. This gives you 1 over 4 and B squared for the van der Waals gas. 8A over 27B minus KBT. So it is like kappa goes like T minus Tc to the power minus 1. Okay, check that. Since it must be T minus Tc to the power minus gamma, gamma turns out to be 1. Okay. You can Taylor expand the equation state around the critical pressures. You find delta equals 3, beta equals 1/2. Because this 1/2 comes from the Maxwell's construct. This goes like Tc minus T to the power 1/2. It comes from there. So we can compare with the experimental values, these critical exponents. Van der Waals results and the experiment for alpha both give 0. Beta is 1/2 from Van der Waals, and experiment says it is around 1,034. For gamma, Van der Waals finds 1, experiment 135. For delta 3 and 4.2. When you look at the correlation between your model result and the experimental result, agreement can be said to be pretty good. So that is enough to conclude that the simple Van der Waals equation of state is enough to understand the phase transition, first order phase transition from a gas to liquid with a Maxwell correction used to correct the unstable region coming from the Van der Waals equation. So that's it. I think it's a nice example, and which can be done by a simple model like van der Waals. Now we have to go to an example of the second order phase transition, which is the ferromagnetism. And the model I will use for this, well, many people use Ising model or Ising model, whatever, okay? That I will do in my next lecture. Then, of course, with the Ising completed, I will go to the further discussion, which is known as mean field theories or Landau theory of phase transitions, a simplified version of the phase transition theory. Now we can stop and discuss if you like.